Hi, we are going to talk about differentiability of a function at a point. So what does it mean? It means that the derivative exists, and one way to understand that is if a function is continuous, it's going to be differentiable if what these are one-sided derivatives. So as x approaches c from the left of this difference quotient, as x approaches c from the right of this difference quotient, these are one-sided derivatives. They both exist and they're going to be equal. So let's take a look at this first example. Obviously we know that this is a quadratic function and it is going to be continuous at x equals 1. So we know it's continuous. We can continue our analysis here. Alright, so what we're going to do is we're going to set derivatives from two sides of 1. Let's go ahead and start with the left-hand derivative. It's going to be f of x minus f of 1 divided by x minus 1. So this is going to be the limit as x approaches 1 from the left of x squared minus 3x and then minus f of 1, which f of 1 is going to be negative 1. Correct? Let's check. F of 1 is 1 squared minus 3. Oh, it's negative 2. Okay. So minus negative 2, so plus 2 divided by x minus 1, which gives you the limit as x approaches 1 from the left. We can factor it. It's x minus 1 times x minus 2 over x minus 1. We can cross out x minus 1 and we're going to be left with x minus 2, and direct substitution works, and it's going to be 1 minus 2, which is going to be negative 1. Let's take a look what happens on the left. I'm sorry, this was on the left. Let's take a look on what happens on the right. So it's going to be f of x minus f of 1 divided by x minus 1 equals the limit as x approaches 1 from the right of x squared minus 3x plus 2. It's exactly the same expression. That's going to equal negative 1 as well. The function is continuous. The one-sided derivatives both exist and equal negative 1. The function is differentiable at x equals negative 1. Oh, I'm sorry, at positive 1. The value was negative 1. Let me just fix this at 1. Alright, here's what the graph looks like. This is the tangent line at that point, and the graph is nice and smooth, and there's a tangent line to that curve. So what about this function? We know this function is also continuous at x equals 2, so we can go ahead and check one-sided derivatives. The limit as x approaches 2 from the left, it's going to be of f of x minus f of 2, which is 0, divided by x minus 2. So it is going to be the limit as x approaches 2 from the left, the absolute value x minus 2 divided by x minus 2. These expressions are almost the same except for the one on the bottom. The top one is always positive. The bottom one, when 2 is slightly, where x is slightly less than 2, because that's what on the left means, the bottom value is going to be negative and the top one is positive. So we are actually going to get negative 1 here. When we are going to do the same thing from the right, let's do that. So as x approaches 2 from the right of x minus 2 minus 0 divided by x minus 2, we're going to have the limit as x approaches 2 from the right of x minus 2 divided by x minus 2. So when we are on the right hand side of 2, the bottom is positive and this one equals positive 1. So they're not equal to each other, and what we're going to have here is the function is not differentiable at x equals 2. Right. This is what this graph looks like. So what can we assume so far, if the function is continuous and the graph is going to be smooth near the point in question, the function should be differentiable, because what happens with this graph has a sharp turn at 2, and the graph before that was nice and smooth. So is that actually true? The function has to be continuous, but what about the nice and smooth curve? Is that always going to be the case? Let's take a look. So here's our function, f of x equal, h of x equals x to the power 1/3. And we know this function is continuous at 0. So we can go ahead and do our work with one-sided derivatives. So we're going to do the limit as x approaches 0 from the left of f of x, which is x to the power 1/3, minus f of 0, which is 0, divided by x minus 0. So it's going to be limit as x approaches 0 from the left of x of, this basically cancels, this is going to be 1 over x to the power 2/3. And when x approaches 0, this is going to approach infinity. And if we try to do the same thing with the other side, you are actually going to end up with the same exact thing, which is going to give you also infinity. And this is not going to work, because we want, well, it's actually going to be infinity either way, but we need finite limits for the limit to exist. Remember that? And we don't. We have infinite values. This function is not differentiable at 0. And what happens here, if you look at the graph, right here I have the graph, at 0 you're going to have a vertical tangent line. So this graph is actually smooth everywhere. It is continuous everywhere, but because of a vertical tangent line, this is going to be problematic, and it's not going to be differentiable at that point. So what can we summarize? So I already summarized this about h of x. So if we want to consider a function to be differentiable, the function must be continuous. Continuity is a necessary condition for differentiability. Differentiability implies continuity, which means if the function is differentiable, it is going to be continuous. So differentiability is sufficient condition for continuity. So here's what we can say so far. If the function is differentiable at a particular point, it must be continuous at that point. If it's not continuous at that point, it cannot be differentiable at that point. If the function is continuous, we don't know. The function may or may not be differentiable, and we're going to have to analyze that. And we're going to look now at piecewise functions, because they make things a little bit more interesting as far as trying to determine if the function is differentiable or not. So we're going to take a look at this function first. We have this. Is it differentiable at x equals 1? Well, since it's a piecewise function and we don't know if it's actually continuous or not, we're going to have to check that first. So the limit as x approaches 1 from the left of f of x is going to equal, well, we take 1, we're actually evaluating the first function, right, because that's when x is less than 1. So it's going to be the limit as x approaches 1 from the left of 2x plus 1, and our value is going to be 3. What about the other side? Limit as x approaches 1 from the right of f of x. We're going to use the second function, and it's going to be 3 as well. What about f of 1? F of 1, we plug it into the first function, is 3. One-sided limits exist, therefore the limit exists. The function is defined at that point, same value, which equals to the limit as x approaches 1 of f of x. The function is continuous. So now we can go ahead and check differentiability. So when we do our left-hand derivative, we're going to do f of x minus f of 1 divided by x minus 1 equals limit as x approaches 1 from the left. So from the left we're using the first function. It's going to be 2x plus 1 minus f of 1 we know is 3 divided by x minus 1. So this is going to give us the limit as x approaches 1 from the left of 2x minus 2 divided by x minus 1. You can actually factor out 2 in the numerator, and you can cross it out, and the answer is going to be 2. So the left hand derivative is 2. How about the right hand derivative? So on the right hand side we use x squared plus 2 minus 3 or x minus 1, which here is going to give us limit as x approaches 1 from the right, x squared minus 1 divided by x minus 1. X squared minus 1 can be factored. Oh, let me just continue this here. Limit as x approaches 1 from the right, x minus 1 times x plus 1 divided by x minus 1, and we divide x minus 1 crosses, and we substitute 1 in here, and the answer is also 2. So we have the same one-sided derivatives, and therefore function is differentiable at x equals 1. Alright, moving on. This example is this function differentiable at 2, so g of x. First we need to see if it's continuous, because we don't know if they actually come together. Limit as x approaches 2 from the left of g of x is going to be the limit as x approaches 2 from the left. We're using the first function when we're on the left of 2 of negative x squared plus 3x. We can substitute, so it's going to be negative 4 plus 6. Negative 4 plus 6, and it's going to give us 2. The other side, limit as x approaches 2 from the right of g of x equals limit as x approaches 2 from the right of the second function, minus 1/2 x plus 3. So substitute this here, and it's going to give us 2 as well. So that means the limit as x approaches 2 of g of x equals 2. G of 2 equals 2. The function is continuous. Therefore, we can go ahead and check differentiability now. So limit as x approaches 2 from the left of g of x minus g of 2 divided by x minus 2 is going to give us limit as x approaches 2 from the left. So it's going to be negative x squared plus 3x minus g of 2 is 2 divided by x minus 2. So we can factor out negative 1 in the numerator, and then it's going to give us, if we factor out negative 1 in the numerator, we're going to get x squared minus 3x plus 2. That means we can actually factor that. It's something that's going to give you x plus x minus 1 times x minus 2 divided by x minus 2. X minus 2 are going to cancel, and then we're going to have negative times x minus 1. We substitute 2 in here. That's going to give us negative 1. Right? 2 minus 1 is 1, and negative is going to give you negative 1. So that's the left hand derivative. What about the right hand derivative? Limit as x approaches 2 from the right of g of x minus g of 2 over x minus 2. Then we use the second equation. It's going to be negative 1/2 x plus 3 minus 2 divided by x minus 2. That is going to give us limit as x approaches 2 from the right of negative 1/2 x plus 1 divided by x minus 2. So what we are going to do here is we're going to multiply both sides, both top and the bottom by 2 to get rid of that fraction. And that's going to give us the following. That's going to give us limit as x approaches 2 from the right of negative x plus 2 divided by 2 times x minus 2. Negative x plus 2 and x minus 2 are going to cross out with negative 1 because they're opposites. And what we're getting here we are getting negative 1/2. Negative 1 here and negative 1/2 here, different values, not differentiable. At x equals 2. Okay. I need to warn you about one thing. This problem here, what's going to happen here is if you try to do the limit as x approaches, we're trying to see if it's differentiable at 1, as x approaches 1 from the left of h of x. That's going to be the first equation. So it's limit as x approaches 1 from the left of 2x squared minus 8x. That's going to give us 2 minus 8, negative 6. Correct? And when you do limit on the right hand side, you are going to get, you are using the second equation, and it's going to give us negative 2. So this function is not going to be continuous, therefore we don't even go for differentiability. We know it cannot be differentiable. Not continuous at x equals 1, therefore not differentiable. I'm not going to show you this, but I'm going to mention this really quick. What's going to happen here, if you actually try to ignore continuity here and go straight to differentiability, what's going to happen is you will see that the one-sided derivatives here are actually going to equal each other. And that may lead you to think that the function is differentiable, but it's actually not differentiable because it lacks continuity there. And so the continuity is something you have to check first all the time. Hi, and this is a typical example of a problem where you have given a piecewise function with some values that are not known, and you want to try to figure out what a and b are going to be to make this function differentiable. The first thing we need to do is check continuity. So as x approaches negative 1 from the left of f of x is going to be a limit as x approaches negative 1 from the left of ax plus b, which is, you just substitute negative 1 here and it's going to give you negative a plus b. And we do it on the right hand side, negative 1 from the right of f of x. It's going to be limit as x approaches negative 1 from the right of x squared minus 2x, and that's going to give us 3. So what we want, because we want one-sided limits to equal to each other, we want negative a plus b equal 3. But we need another equation because we have two unknowns. So now we're going to do differentiability. Limit as x approaches negative 1 from the left of f of x minus f of negative 1 over x plus 1. It's going to give us limit as x approaches negative 1 from the left. F of x on the left is ax plus b. When you substitute negative 1 in there, we already did it earlier, is going to be negative a plus b over x plus 1, which is going to give us limit as x approaches negative 1 from the left of ax plus b plus a minus b over x plus 1. So b's are going to cancel. And then we can factor out a, right? And we're going to get that the limit as x approaches -1 from the left, a factors out, x plus 1 divided by x plus 1 is going to give us a. So this is the left hand derivative. What about the right hand derivative? So now we're going to do limit as x approaches -1 from the right of f of x. So it's the same expression. So here it's going to be x squared minus 2x minus, when you substitute -1 in here you get 3, so minus 3 over x plus 1 is going to give us limit as x approaches -1 from the right of, here we're going to have x minus 3 times x plus 1 over x plus 1. X plus 1 is going to cancel. And we are going to get -1 substituted in here. The answer is going to be -4. We want these two values to equal each other, which means a equals -4, right? And then when we take this value and substitute it in here, we are going to be able to get the value of b, and b is going to be -1, right? And that's how you do problems like that.